Hi there. I hope y'all had a fantastic weekend. We're going to continue our study with row reduction, and let's go ahead and begin. In the last video, we talked about echelon form. We talked about leading entries. The leading entry, again, is the first non-zero entry in a row. So in row 1, our first non-zero entry is this 2. In the second row, our first non-zero entry is this 1. And in the third row, our first non-zero entry is this 5. But because leading entries are based on rows, some columns may get left out. And so some columns may not have a leading entry. These columns tell us some information about the system. We will look at them in more detail over the course of this video. But our terminology is that a column that does contain a leading entry is called a basic column, and a column that does not contain a leading entry is called a free column. So in this matrix here, columns 1, 3, and 4 are basic, and columns 2 and 5 are free. So in this matrix, which columns are basic and free? Basic columns are 1, 3, and 4, 1, 2, and 4. I messed that up. 1, 2, and 4. And the free column is 3. Will every matrix have a free column? And that doesn't have to be true. We can have a matrix like this. And these are our leading entries, 1 and 7. And every matrix has a free column. And so this is not necessarily true. But lots of matrices do have free columns. If we are working with a system of equations, then a variable in that system that corresponds to a basic column is called a basic variable, and a variable in a system of equations that contains to a column, corresponds to a column without a leading entry, is called a free variable. So we're using the same terminology, basic and free, but we can apply them to the columns of the matrix, or we can apply them to the variables in the system. Here's an example that shows what I mean. If we look at this system of equations, then this system of equations corresponds to this augmented matrix. The top row is 1, 3, negative 1, 0. The middle row is 4, 1, 7, 11. The bottom row is 2, 0, 4, 6. And if we take the time to row reduce that, this matrix is the echelon form of the matrix that's above it. And we have leading entries in columns 1 and 2, but we don't have a leading entry in column 3. So we could say that the column of this matrix is free. But we could also say that the variable that corresponds to that column, which is x3, this variable is free. So we can do this either way. And we have a theorem about freeness. If the last column of the augmented matrix of a system is basic, then that system of equations has no solutions. We will see examples of all of these in a little while, but let's keep going. If the system has a solution and at least one free variable, That freeness of the variable is what enables the system to have an infinite number of solutions. But if the system has solutions and every variable is basic, then there's only one solution to the system. There's no freedom in the system, and therefore we only have one solution. In order to write out the set of infinite solutions, we use a special kind of echelon form called reduced echelon form. Reduced echelon form is a more stringent version of echelon form. A matrix is in reduced echelon form if it's already in echelon form and meets these additional conditions. All of the leading entries are the number 1, and all of the leading entries is the only entry in its column. So now we're engaging putting zeros in the columns as well, so that the leading entry is all by itself. I'll show you an example. These matrices are in reduced echelon form. It says their leading entries are circled, but I didn't do that. I'll circle them now. These are the leading entries in the first matrix. Both leading entries are equal to 1. And in the columns that contain the 1, the other entries are zeros. So the columns that contain the leading entries, the leading entry is the only thing in that column other than 0. In the second matrix, these are my leading entries. All of the leading entries are 1. And in the columns that contain a leading entry, the other entries in those columns are all zeros. Another way of thinking about reduced echelon form is that the columns that contain a leading entry are this is going to use some terminology from the very first day. Our standard basis vectors. This column right here, 1, 0, is the vector E1. This column is a vector E2. This column is E1 in R4, E2 and E3. So that's another way of thinking about echelon form, is that our leading entries represent standard basis vectors, which we know are easy to calculate with. Any matrix that's already in echelon form can be reduced to reduced echelon form using a process known as the backward phase row reduction algorithm. We call it backward phase because we work in reverse order. We start with the last leading entry and then work our way back to the first leading entry. So we're going to start with a matrix that's in echelon form. Let P be its last entry, leading entry, the one that's the furthest to the right. We'll use linear combinations to replace all of the entries above P with zeros. And then we'll divide the row by whatever P itself is, which makes the leading entry into 1. If we're not at the beginning of the matrix, then we let P be the next rightmost leading entry and go back to step 2. Let's give this a try. I have a matrix that's here that's already in echelon form. We're going to use the backward phase row reduction to put this matrix into reduced echelon form. So these are my leading entries. And because this is backward phase, we're going to start with the leading entry on the end. We're going to start here. Oops, sorry. So what we're going to do is we need to change this 2 to a 1. And we also need to change these entries to 0. So let's try a couple of things. We'll take this 2 here, and we're going to divide this row by 2. So we're going to take row 3 divided by 2. That's going to give us the matrix 3, 5, 2, 6, 0, 6, 1, 2, 0, 0, 1, and negative 4. And then from there, I'm going to cancel this 2 by subtracting twice row 3. So row 1 minus 2 times row 3. And we're going to take row 2, and we're just going to subtract row 3. So that's going to give us 3, 5, because I'm subtracting zeros from those. 2 minus 2 is 0. 6 minus a negative 8 is 14. It's negative 2 times negative 4 is positive 8. That makes us into a 14. Then in the second row, 0 minus 0 is 0. 6 minus 0 is still 6. 1 minus 1 is 0. 2 minus a negative 4 is positive 6. And notice that this column is now a standard basis vector. This is E3. So we're making some progress. We're now going to move backwards to this leading entry. We have to change the 6 to a 1. And then we also have to change this 5 to a 0. So an easy way to change this 6 to a 1 is to divide the entire row by 6. We'll take row 2, divide it by 6. That's going to give me 3, 5, 0, 14. 0, 1, 0, 1. 0, 0, 1, 4. Then the top row, we have to subtract 5, so we'll take row 1 minus 5 times row 2. And that'll cancel out the 5. So 3 minus 0 is still 3. 5 minus 5 is 0. 0 minus 0 is 0. 14 minus 5 is 9. And now this column is our standard basis vector E2. So we work backwards to our first leading entry. And we have to change this leading entry into a 1. And that's easy. We'll take row 1 and divide it by 3. And that gives me 1, 0, 0, 3. 0, 1, 0, 1, 0, 0, 1, and 4. And now this matrix, all of my leading entries represent standard basis vectors. And this is now in reduced echelon form. I told you that standard basis vectors are easy to calculate with. Imagine that this was a system of equations. This first equation up here would represent (3x plus 5y plus 2z equals to 6). But this equation just represents 1x plus 0y plus 0z is equal to 3. I'll actually write the zeros here for a second, which just says x is equal to 3. In other words, the reduced echelon tells me the exact value of x in this case. X is 3, and the second row tells me that y is 1, and the third row tells me that z is 4. I have the solution if I have the reduced echelon form in this case. Every matrix can be reduced into reduced echelon form, and furthermore, there's only one answer to how we reduce to reduced echelon form. If you and your friend start with the same matrix and you are both row reducing it, you will both get the exact same reduced echelon form. There's only one reduced echelon form for any matrix out there. And so the reduced echelon form is uniquely determined by the matrix. All right, we're going to try to solve this system of equations. 2x minus y minus z is equal to 3. X plus 3y plus z is equal to 1. 7y plus 3z is equal to 7. And this system of equations has this augmented matrix. This is not yet in echelon form. So we're first going to have to put it to echelon form, which means we have to work forwards through the matrix to get our leading entries. Our first leading entry is going to be a 2. We'll have to clear the entries underneath it going forwards. So I'm going to have to change this 1 into a 0. We can do that by taking 2 times row 2 minus row 1. 2 minus 2 is going to give me 0. 2 times 3 is 6, minus a negative 1 is plus 1, which is 7. 1 minus negative 1, or 2 times 1 is 2, minus negative 1 is going to give me a 3. 2 times 1 is 2. 2 minus 3 is negative 1. So now this entry is the leading entry. This is a leading entry. But I have 2 leading entries in this column, so I have to move this 7 out of the way. So I'm going to take row 3, subtract row 2 from this. And when we do that, we get 0 here, because 7 minus 7 is 0. We also get 7 here. 3 minus 3 is 0. And then we have an 8 here. 7 minus negative 1 is 8. And now we are in echelon form because our leading entries move left to right. But what does this last equation say? This last equation says that 0x plus 0y plus 0z is equal to 8, and that can't happen. And because we have found ourselves to have an impossible equation, the correct solution is that this system of equations has no solutions. There are no values of x, y, and z that make these equations true. So anytime we see a row in an augmented matrix that looks like zeros on the left side and any non-zero value on the right side, so that it represents an equation that looks like 0x, 0y, 0z equals b, that's impossible to solve. But this says that a leading entry is in the augmented column, and that makes the augmented column basic and not free. If the augmented column is basic, the system has no solutions. Or we can say that the system is inconsistent. There's no way to make the equations come to an agreement. There's no solution that doesn't work with that. All right, let's move on. We're going to solve this system of equations here. (3x plus 4y minus z is 1, 2x plus y plus z is 9, x plus y is equal to 2. And this is the augmented matrix for this system. Once again, it's not in echelon form because all of my leading entries are vertical. They need to be left to right. So I'll first cancel out the 2 and cancel out the 1. So push those leading entries a column over. Let's take a look at what happens. To get rid of this 2, I'm going to use the lowest common multiple of 2 and 3, which is 6, which means I have to multiply this row by 3 and this row by 2 and subtract them. So 2 times 3 is 6, 3 times 2 is 6, 6 minus 6 is 0. 3 times 1 is 3, 2 times 4 is 8, 3 minus 8 is negative 5, 3 times 1 is 3, 2 times negative 1 is negative 2, 3 minus negative 2 is 5, 3 times 9 is 27, 2 times 1 is 2, 27 minus 1 is 25. Then the bottom row, we're just going to take the bottom row times 3 and then subtract the 3. We don't have to find the lowest common multiple here. And we get 3 minus 3 is 0, 3 minus 4 is negative 1, 0 minus a negative 1 is positive 1, and 6 minus 1 is 5. So here are our leading entries now. This is still not an echelon form. We're going to have to get rid of this negative 1. So we could do that by taking 5 times row 3 and subtracting row 2. Negative 5 minus negative 5 is 0, 5 minus 5 is 0, and 25 minus 25 is 0. And the whole row turned into all zeros, so we only have 2 leading entries. But this is echelon form because the leading entries are left to right. But we have a free variable. Z in this case is a free variable. To work with this free variable, we're going to keep reducing this all the way down to reduced echelon form. So we now work backwards, starting with the last leading entry, and work backwards to the first leading entry. We go forwards to get to echelon form, then we go backwards to get to reduced echelon form. So this negative 5 needs to change to 1. So I'm going to divide the entire row by negative 5. And that gives me a 1 here. Now I need to clear out that 4 so that this is a standard basis vector E2. So we'll take row 1 and subtract 4 times row 2 from this. And that gives me 3, 0, 3, 21 in the top row. Now this leading entry also has to be a 1, so we're going to divide this row by 3, and we'll end up with 1, 0, 1, 7. 0, 1, negative 1, negative 5, and so on and so forth. This matrix is in reduced echelon form. So on the next slide, I'm going to clear out all of this scratch work. I'm going to keep this matrix right here, and we're going to talk about the reduced echelon form. I'm just clearing out some of the clutter. So let's talk about what's happening here. This is saying that the vector x times E1 plus the vector y times E2, plus z times this other vector that's not one of the standard basis vectors is equal to the vector 7, negative 5, 0. And what we want to do is we want to come up with a way of turning this into a standard basis vector. If we could make this into an E3 somehow, that would make this problem easier to solve. Is everyone okay with that? So what we're going to do is we're going to introduce a new variable called whatever you want to. We could call it t. And we're going to make t and z equal to each other. Z and t are equal to each other. But that means that t minus z is equal to 0. And if I introduce a new column for t, that would be 1 for t, and negative 1 for z would be equal to 0. And that would be, I'll use that row instead of the row that just tells me that 0 adds up to 0. That will be a vector E3. So we have x times E1 plus y times E2 plus t times E3 is equal to 7, negative 5, 0. And that's easier to solve. So let me walk through what's going to happen here. T and z are the same. So I'm going to rewrite this equation as x, instead of plus z is equal to 0, I'm going to say x plus t, I'm sorry, not 0, 7. And then y minus t is equal to negative 5. And z is equal to t, or z minus t is equal to 0, either one, because they're the same. We're going to solve each equation for x, y, and z. We're going to get x, y, and z by itself. So x is equal to t plus 7, or minus t plus 7. Y is equal to positive t minus 5. And z is equal to t. And now we'll take this set. This is one way of writing the solution. We know what x is, we know what y is, we know what z is. For any value of t, we can plug in a value of t and we can get a solution. But there's something we can do even further with that. I'll go back up here. We can write this as a vector. The vector that contains x, y, and z is equal to the vector that contains negative t, 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 and the vector that contains 7, negative 5, and 0. And I can factor out the t from this, which is t times negative 1, 1, 1, plus the vector 7, negative 5, 0. And this solution is called, let's try that again, parametric vector form. These are just two different ways of writing the solution. And you should be able to recognize both of them. So what I want to do with the rest of the video is let's get some practice writing some parametric vector form. Okay? So here's another example. We're not going to do the row reduction here. This augmented matrix is already in reduced echelon form. And we're going to use the variables x1, x2, x3, and x4. So the equations as they are written here are x1 minus 4x4 is equal to 3. x2 plus 2x4 is equal to negative 5. And x3 plus x4 is equal to 6. And x4 itself is free. When I have a free variable in the system, I assign it to a new letter. So I can say x4 is equal to t, but I can also say that x4 minus t is equal to 0. That's the same thing. And when I use this new variable, the t, the parameter, then these equations now become x1 minus 4t is equal to 3, x2 plus 2t is equal to negative 5, x3 plus t is equal to 6, because all I'm doing is I'm just replacing x4 with t, but then I have this last equation that says x4 minus t is equal to 0. And now I have 4 equations instead of 3 equations, and I can solve for each of these 4 variables. And so my solution is going to be that x1 is equal to, I'm going to bring the t to the other side so it becomes positive 4t. x2 is going to be negative 2t minus 5. x3 is going to be negative t plus 6. And x4 is going to be positive t. That is our equation form. We can write this in parametric vector form as the vector x1, x2, x3, x4 is equal to t times the coefficients here, 4, negative 2, negative 1, positive 1, plus the constant terms, 3, negative 5, 6, and 0. So if we have a free variable in the system, we assign that free variable to a separate letter. We call that other new variable, we call it a parameter. And that enables us to write a fourth equation in the system so that I have an equation for each of my 4 variables. Let's try another example. Let's try this system here. A lot of variables here. In the interest of time, I'm not going to do the row reduction in the video, but it is on page 39 of the book. And so you can look up the row reduction steps yourself. But what we find is that I have leading entries corresponding to x1 and x2, and I have 2 variables that are free. x3 is free, and x4 is also free. And so I'm going to need to assign them both to letters. I can't call them both t, so I might call one of them, I might say that this one is s, and I might call the other one t. Or I might use t and u instead of s and t, but I have to choose separate letters for each of them. And so the first equation will read as x1 plus 4 times s minus 2 times t is equal to 3. The second equation is x2 plus 1 times s plus 3 times t is equal to 2. And I have equations now for x1 and x2. I need an equation for x3 and x4. But I have them right here. x3 is equal to s, so x3 minus s will be equal to 0. And x4 minus t will be equal to 0. That's how I fill out my extra 2 equations, so I have an equation for each variable. I now get these variables by themselves, which means moving everything to the other side. And so x1 is going to equal to negative 4s plus 2t minus 3. x2 is going to equal to negative s minus 3t plus 2. x3 is going to equal s, and x4 is equal to t. Or using our parametric vector form, where we combine everything into vectors. The vector that contains all 4 of my variables is equal to my parameter s times negative 4, negative 1, positive 1, 0, plus t times the vector 2, negative 3, 0, and 1, plus some constants, negative 3, positive 2, 0, and 0. And so this is a system that had 2 free variables, and so we needed 2 parameters. All right. We're going to wrap up this video and start on something new next time. Thanks for coming.